last time we talked about trees, if we recall. Right? So a tree, in a normal tree, right, we have what are called nodes. We have a root. We have leaves. We have children. Right? So all different terms that we use to talk about a tree. So last time we described the issue of having a tree where suppose we inserted all of the data into our tree and it was sorted. Biggest to smallest, smallest to biggest. What did we say our list devolved into? Or our tree devolved into? Shouldn't give away the punchline when I'm saying the joke. All right, it devolves into a list, right? Because if we keep adding always to the right-hand side, we end up with something where our search time is not O of n log n, or log n, right, to search the tree. Right, it's O of n over 2 or O of n, right? So what happened was people said, hey, I wonder if there's a way where we can make it so that the tree, right, kind of rejiggers itself. So if we have a in-order listing of all of our nodes, theoretically what we could do is if we had a list of all of them in order, we could pick out the one that's in the middle and make that our root, right? Because then half of the stuff is going to be on the left and half of the stuff is going to be on the right. And then we could keep doing that process, right? Pick out the middle one, pick out the middle one, right? So if they're all sorted, we could go through that process. But they said, well, that's a lot of work, right? Because we got to sort them. Sorting is a sort of known expensive thing, and we'll talk about sorting sooner than later. So I said, is there a way where we could make it so that the data structure would automatically sort of fix itself? So and here they talk about in 1972, somebody came up with this thing called a B tree, right? And basically what we have is we have a special type of tree called a red-black tree. Called red-black because, as you can see in the picture, we have nodes that are either colored red or purple. I mean black. Oh, almost. Right? So there's a couple properties. You can see the properties that are here on the side. Right? Number one, you're either red or black. Okay, that's pretty simple. The root is black. Okay. All leaves. So if we go down to leaves as in the null pointers, right? All leaves are going to be colored black. Right? And if a node is red, number 4, then both of its children are black. And so that's a requirement. If you're red, then both of your children have to be black. Okay? And then number 5 is, okay, any path from a given node to any of its descendants contains the same number of black nodes. Right? So the only way a node can be red is if it's got 2 black children. And the number of, starting from any node, right, so given a particular node, the number of black nodes down to any leaf is the same number. So if we look at going down this, right, so we got 1, 2, 3, 1, 2, 3, right? So any path that I take, I have in this one, I have 3 black nodes, okay? Again, this is like, okay, well, that's kind of weird. But what happens is, when we start inserting a new node, basically, when we insert the node, we, what's called recolor the tree. So as we insert new nodes, we always color the new node that we put in black, and then we go through and we do what are called rotations. So we'll see the properties of rotations. But basically what's going to happen is, as you start inserting nodes, it's going to say, oh, at some point I'm out of balance, right? And I need to do a rotation so that my tree goes from being out of balance on one side because I inserted a node on one side, right? It gets too heavy and then we rotate it back. And we keep doing that property as we go up. So let's see if I don't know if they, here's an example. All right, so if we end up with a coloring such that we have, right, so we have this node G, we got P, N, and U. So what happens is in that one, we just do a recoloring, right? So we change the nodes P and U to as you can see, black, right? And this one becomes red. Or if we look at this one, we're going to take, we got G and G has the children P and U and N, and why is that? Does anybody remember? Given the rules, why is this a problem? What is the property of a red node? Both of its children are black. Okay? So here we're going to do a rotation, and then we'll do the recoloring, right? So if we look at this, you do the rotation, and then you recolor, right? So that you have the proper coloring. So the rotation is going to sort of fix some of that imbalance that we have. So it might be hard to think about that. So let's, there's a really nice visualization here. So I'm just going to insert things in order. And I think, let's see. I can't remember if there's a animation speed. Let's slow it down. Okay, so every node that we insert, right, is going to be red, and then we go ahead and recolor, or sorry, black, and then we recolor. So I got 1, 2. Right, so then it did a rotation, because it basically found to the point where a condition existed where we go and talk about looking at uncles, right? So if you're red and your uncle is red, then you're going to do a rotation. Right, so every time I insert, so I got 1, 2, 3, decides where it's going to go, then it possibly recolors, right? And if we go ahead and show no leaves. All right, so if we look at this, right, one of the properties, every path to a leaf, we have the same number of black nodes, right? So in this one, we have 3 is our number. Right? So every path, there are 3 black nodes. Let's see, 4. So again, it's got to decide where it's going to go, right? So you can very easily write a recursive algorithm that does that. And then it basically had the property where it was out of balance, did a rotation, right? So I've been inserting these in order, right? If we did our normal binary search tree, right, and we just did our insert how we do it, we'd end up with a list if I did those inserts, correct? That makes sense? Okay, so you can keep going, and basically this would, you can see that it's going to, right, keep adding these and keep doing rotations. I think if I get to, let's see, 7. Right, so when we had 6, we had sort of the most imbalance where we could go down one path and it was sort of 2 searches. We go down another one and it was 4, right? So it was within, it was 2 more. But that is the worst case, right? So every time I keep adding stuff, right, I'm not going to get any worse than this.
So in doing something like this, is this where we would need to keep track of parents and all that, whereas the other one we so we didn't keep track of parents?
Would we need to keep track of parents? So, in a sense, you need to keep track of parents, but here's the deal. So when we're doing this, we would write it as a recursive function, and the fact that each recursive call is going to keep track of its current, say, parent. So when you come back up from one recursive call, you have the information of who your parent is as you're doing that. So you could do that, or we could keep track of parents, but typically they don't. Because the fact that I'm doing a recursive call, right? Because if I do this insert, right, I'm going to insert, and I'm going to keep calling insert, say, 4 times. And as I come back up, I do the rotations. And so you don't have to actually keep track of it because it's sort of implicitly kept track for you. But yeah, that's a good That's a good question, right? So that would be another way to do it, is to keep track of who your parent is. But then adding that, you're going to add another pointer. So that's additional storage. And you're going to have to update those every time, right? So you're going to end up with, instead of one update to change a node, you're going to end up with 2 updates to change every node. So that's a good question. All right, so this is sort of, if you guys have programmed in Java, so if you ever use the tree map or tree set, these are going to implement these using red-black trees. And so that's what they actually use on the back end. Right, so if we have this property that every time we're inserting, so if we think about the insert, what is the worst case insert time? So how long is it going to take me to insert a node if we don't do rotations? I mean, we're doing rotations, but I'm not counting the rotation in our insert time. How long does it take to get to the farthest leaf from the parent if we have a mostly balanced tree?
0 log n.
What?
0 log n.
0 log n.
O log n.
Oh.
Yeah.
It's like, why are you saying 0?
Yeah. My bad.
Log n, right?
Yeah.
So log base 2 of n. So I think it's ln for log base 2. Right, so log base 2 of n. So whatever n is, if you do the log of it, right, we said that was our search time. Well, our insert, we're going to go down the longest branch, right? I went down the longest branch, right, got to the bottom, and that's where I inserted my node. And then we do rotations. We're only going to ever do one rotation at any level, right? So the last one we saw, we only did one, right, rotation that we ended up doing. But we have to come back up the tree. So if we come back up the tree, how long does that take? Somebody other than Spencer? I go down, it's log in. I come back up.
Oh, log in.
Oh, log in. Good job. Way to pay attention, front row. Right? So we got log in to go down, log in to come back up, and each of the operations in the middle are going to be of a sort of constant time, right? So when we're going to do a rotation, we're basically doing some comparisons, right? We're going to compare our uncle's color to our color, right? We're going to maybe change 3 or 4 pointers at any level, right? So if we say it's 4 at every level, right? We got login to insert, all the comparisons, login to come back. So that's 2 login, which is big O of what? When we talk about big O, we get rid of constants.
Log in.
Log in, right? Well, that's pretty good, right? Log in to just find something in there. Log in to insert something in there. Right, that's a lot better than, think of our list. What was our list to insert? N. And to find?
Huh?
And to find something in our list?
Is it n times n over 2?
Well, no, that's not to find. To find is just to go through the list and find your thing. Even if it's sorted, what is the, how long does it take you to get through it? Average of n over 2, which is big O of n, right? However big n is, that's our time. Right, so we can see that, like, some of these are good and some of these are bad. Now, if we think about the case of our stack, right, would you implement a stack using a binary search tree or using a list? List, right? What was the time to insert on our list if we're doing a stack? 1, right? And remove 1. Right? So we've got to look at the context of what we're doing in order to pick out what is the best data structure in order to store that. Right? And then there's going to be some properties. So we'll talk about, there's going to be one sort of other big algorithm that we'll talk about, and that'll be hashing. Right? So using, in Java, we have the hash map and hash set. right? And those are actually going to provide us with even better time than this login, which login is really cool, but hashing is better, right? But there's a couple other properties that we might want that hashing won't give us. So one of the things we have with this is, remember, what did we talk about? What are the different traversals that we can do? We reviewed it last time and people forgot, so maybe we should review it again.
Post reversal.
Post-order traversal,
Pre-order.
pre-order, in order, right? So if we do an in-order traversal of this tree, what do we get? What's the algorithm for in order? No, the video didn't cut out. There are just crickets.
If your left child is not null, then you go to your left child.
Okay, so if your left is not null,
Yeah.
you go visit it, and then what do you do?
Check again.
No.
What?
You go down the left branch, visit your left,
Right.
and then you visit
So,
yourself, and then you visit your
right.
right. Okay, so we're at 3. Okay, go to the left. Go to the left. Right, okay, no. So we get 1, 2,
6, 3,
3.
3.
Did I put 3 in twice?
Yeah.
Whoops. 1, 2, 3, 3. Right, so this allows duplicates, right? It's kind of weird. Well, we don't actually visit 5 yet. We visit 4, 6, 7. So if we do an in-order traversal of our tree, we end up with the sorted, right? It's in order, right? We actually get the values out of it. Now, when we're going to talk about hashing, right? That's not something hashing can do, right? Hashing does not have the ability to say, what is the thing that, what is the in-order traversal of this set, right? It's like, I don't know. You wanted me to do hashing, so I have no idea what you're talking about. We also have the property that if we, so here I put all of these in like very specific order, right? I did 1, 2, 3, 4, 1, 2, 3, 4, right? But if we had a sparse setting, right, where we said 1 to 100, 5 million, a billion, right? We could put those all in a tree, and they would fit fine. We'd also have the property that we could say, what is the thing that is just bigger than 100, right? It's like a million. Well, in hashing, we don't have that ability. We just know, is it there or not? Yes or no. I can access it really quickly. This we can say, what is the next highest key? Or what is the next smallest key, right? So actually, if you make a project in Java and you use its tree set, you can go and grab a key and say, give me the next highest key. And it'll give you the next one that's higher than that, right? That might not seem very useful, but I can give you an example. When I was programming, so I had to basically write a program that would take this PDF, right? And I had never done PDFs before in my life. And inside the PDF, right, we had little tags that said, if something is red, then it's what we call the price, which is one, there are several different types. Some of the prices were left aligned, some were right aligned, some were centered, right? And when I take the price and I would multiply it by some value. Because I didn't realize this, but in the Midwest, right, we have really cheap cost of living in the United States. And as you progressively get closer to the coast, right, the prices of things go up. Right? This is a weird concept to me, but that's the way it is. Right? So when we would make a catalog for our product, I could sell a product for $100 here, and if I go with that same product and I sell it in New York, I could sell it for $200. Well, that was great for me to make a catalog for me and then make a double-priced one, right, for them. Then they could sell it, same product, it'd be reasonable. But the problem was you sort of go in between, right? So it gradually goes up. It just doesn't spike at 2x when we get to the coast. So we'd have customers that say, yeah, I can't make any money on your 1x catalog, and your 2x catalog is too expensive, right? So I can't sell your product very easily. So we said, well, how can we make it so that you can make your own catalog? So that was my job, right? To make it so they could make their own catalog. So what I would do is I'd go and find all of the prices. Well, there's this weird thing about fonts, where fonts can either be monospaced, where every letter takes up the same space, like a W takes up the same space as an I. Well, when you read stuff and it's in monospace, that's great for us programmers, but for normal people like, dude, that looks terrible. So they have this thing called kerning, where they'll take a pair of letters. It's called kerning pairs, where you take two pairs of letters and see how close they should be to each other. And you've got some weird ones where, like, I don't know if you guys have ever seen this, where like an F and an I are sort of together. I don't know, have you guys ever seen that? It's kind of weird. F-I. Caps lock is on. Let me see if I can find.
Or you'll see like FF together, like.
Well, there's one where it's like the I of the I is the bottom of the F.
Really?
Yeah. I'm not, let's see. But basically, some of this boils down to the way that they used to have to, when they would make these blocks, right? So when they would use to typeset things, they would actually have, some of them would have an overhang on them, so that it would overhang onto the next letter because the T was too big and they had a certain space for each one of their blocks in their font. Right, so anyway, this is a whole subject you can go and look into and learn about. But basically, for every single font, if I wanted to know in a PDF, it would only do a alignment on the left-hand side. Like it wouldn't actually do a right-hand line and then draw the text, so it would always do left-hand. So if I was taking a price and I was making it bigger, I needed to figure out where and I wanted it justified, I'd have to go and figure out, okay, how wide is it? So I know where the end is, so then I can put this new text that is a little bit bigger so that it's aligned on the right-hand side. Anyway, so I'd have to figure out, well, which font am I using so that I can replace it with the right font? Well, in PDF, you can define what a font is. It's kind of like a variable. And you'd say font F1. And then later on, it'd say font F1 is a new thing. And then later on, it'd say font F1 is a new thing. So I had to make a map that said, okay, what is F1 at this location? And I find every time that I change it. And then I'd go and look at, okay, I'm at this location. What is the closest F1 to me? Right? So I'd have to go up and look, and I'd have to find the lowest key that wasn't bigger than the key that I was looking at, where I was being defined. Right? And so that was something that I had to use a tree map in order to do, and I had to use give me the key that is lower than this key, this value that I'm looking at right now. And it would return that. So anyway, when you get into business, you have to deal with weird things like fonts and kerning, and it's not very well defined. Oh, I wish I could.
They're on top of each other.
They are. It's like,
That'd be letting.
what?
I think that'd be letting.
Is that letting?
Go type FI ligature.
Lucky fish suffocate. Oh, nice.
There. Go images.
Oh, images?
Oh, there it is.
Yeah, there it is. Right? So it's like the dot of the I is the little bulb on the F, right? I never realized that was a thing. There's also one with like a T, F and a T or something that are together. I was only dealing with numbers, so I didn't have a lot that I had to deal with. TH. L, FL, that was another one I remember now.
Oh, it looks like an A.
It's an L, it's an F and an L. Anyway, there's stylistic ligatures. Okay, so I'm not an expert in fonts, clearly. All right. Yes.
I have a question.
You have a question. That's why you raise your hand, right?
Right. let's say we wanted to do like divide and conquer. Would we use a tree map, or like would any like list work? Does that make sense, or is there?
So you want to use divide and conquer to do what?
Find a value. Let's say like
Hypothetical.
yeah, hypothetical.
Like there was a question or something that would ask you about finding a value using divide and conquer? If only. Right, so there's a couple different ways that you could tackle this. So I think when we talk about sorting, we'll end up talking about, let's suppose we have all our data in a big array, right? So if you're looking at having all of your data in a big array, a divide and conquer algorithm would be, I'm going to take this problem, divide it into half, right, and solve the one half, and then divide it in half again and solve the other half, right? So we're solving each one separately. So if we think about that, how many times could you take a problem and divide it in half and solve that sub-problem? So let's say it's 8. Divided in half, I get 2 4s, right? Okay, now I divide each 4 in half. Divide each 2 in half. I get it's 1. So how many times was I able to divide that in half?
N minus 1.
3, right? Right? Is that right? Okay, now let's say it was 16. Divide that in half, divide that in half, divide that in half, right? 4. What if it's 32? It's 5. What are these magical things? What? Log base 2, right? So the benefit of divide and conquer is, well, how many subproblems do I have to solve? How far down do I go? I go down log of the size of my problem, but I might do, let's say, n operations in that, right? Okay, so if I do n operations at any level, and I got log of them, if I total that up, what is my total? N operations log times n log n, right? So n log n is at the current point, right? If we take into consideration both space, right? I can't just use infinite space, and time. N log n is the fastest that we can do this, and we'll talk about it, right? So as we do divide and conquer. So divide and conquer, right? So this, if we look at what we did here, when we inserted into this tree, so if we said at any point when we insert a node, how long does it take? No, one node, I insert. How long does it take to insert it? Log n. And I have how many things that I insert into my tree? N. So I do log n operations n times. What have I just done? N log n, right? So if I'm inserting data into this list, right, my time to insert stuff into this list is n log n. And now I've got it sorted, right? So it depends on how you're solving the problem. So if we already have the data already in an array or something, right, we can use some divide and conquer algorithms to reduce the time that we do it, right? And we'll talk about the worst ways to do it, right? Like bubble sort is really terrible for lots of reasons. And if you want to look at it before we talk about it, sort. There's one really good site. Is this it? No, this is not it. Oh, here it is. Yeah, I'll do this one. They're showing all the algorithms going and which ones are the fastest, right? We saw a whole bunch of these, and you can watch them all. Like Let's watch them all versus random. All right, who's done first? Who's done first? Looks like he. And then the other ones are really quick, right? Quick sort. Hey, it goes quick. And we'll talk about all these different algorithms, right? So that'll be part of what we talk about. But some of these are divide and conquer, like shell, merge, heap, quick 3. Some of them are not. Insertion sort. Insertion sort, you find the smallest thing, put it at the beginning. Find the next smallest thing, put it at the next beginning, right? Insert stuff in the right place. Bubble sort, you switch values as you're going, you just keep swapping them. Right? Bubble sort does really bad on reversed. Look at Bubble go. Come on, Bubble. Come on, Bubble. Oh, you beat selection. Oh, good job. Right, so this is kind of fun to watch. But anyway. All right. So did I answer your question, Jonah, or did I just let you go on?
Yeah.
Okay.
It just depends on how you implement it and what you have already.
Yeah, and as you look at this, right, these algorithms perform differently based on what you're doing. So nearly sorted, Bubble is near the top, right?
Shell, really?
Yeah, they. I guess I can't hit it unless they're done. Okay. Yeah, insertion was fast. Shell and Bubble were fast. The other ones took a while. Selection is like just terrible, right? In that case. Right, and when people write their first algorithm, right, they'll write bubble sort, and then they'll figure out that maybe they shouldn't do that. But anyway, I like the visualization because it kind of shows it to you. But typically you have stuff like this, like random data, and you're trying to sort it, and bubble is pretty bad for that. So. All right. So questions on red-black trees? Right, they actually give you some code that looks strikingly similar to C code. I don't know how that works. Imagine.
Like the balancing goes off the color. Does the balancing go off of the color?
Yeah, so the balancing uses the color in order to decide which different cases that you're going to do. So basically, if I recall correctly, it talks about here are some of the different ones. If the parent and the uncle are red, right, we have to handle that case. And if its parent is red and its uncle is black, then we also have to do that. So basically, if its parent is red and we've added a new node, right, we've added another black one to the tree, right? Because that means that its other child is black, so we need to do a rotation. So there's several different cases. Basically, if you code this, right, you have to handle all of these different cases, right? And they go through the code in here, right? Example C code. Wow. Well, that's exciting. So I don't know if there's necessarily use in making you do something that there's like a whole bunch of nice source code for, but at least we should understand that. Okay? So if you use any of the modern sort of languages and libraries, they have this built in. So I mean, that with a lot of these things, right, I made you guys do a stack, but right, stacks are included in Java. If you look at C++, right, they have these standard template libraries. They include all of these different algorithms that you can use when you're programming. But part of the point of doing an exercise is for you to get sort of how do you do this. The other one is for you to understand, right? Why we care about all this is I give you a problem, you need to find the most efficient solution to do that. Sometimes it doesn't matter, but sometimes it does, right? Sometimes it needs to be fast. And you can't make something fast if you don't know why making a certain selection is good or bad. So, any questions? It's Friday, it's a beautiful day. Go enjoy the weather or go to another class. Whatever floats your boat.